section 9.1, or inverse variation. Before we can start a discussion about inverse variation, we need to review an Algebra 1 concept that is direct variation. You know, back in Algebra 1, you talked extensively about y equals mx plus b. If b becomes 0, you get the equation y equals mx. This is what we refer to as direct variation. And for some reason that I don't quite get, we decided that we wanted to change the letter m to the letter k. So we use a lot of y equals kx when we talk about direct variation. Now this letter k, which was the slope of the line, this letter k, is what we refer to as the constant of variation. So what is the slope of the line? So here we have our first graph, or our first example, that says the graph of a direct variation function passes through 1, 0. Write the equation. So I am giving you here x, y. Like we do in so many cases, now plug it into the equation and solve for what you need. So I am going to plug 10 equaling k times 1. So k clearly equals 10. So what is my equation for this particular example? Y equals 10x. There's my direct variation equation. All right, now truly heading into inverse variation. Inverse means put something in the opposite location. So inverse variation is equal to y equals a divided by x. Now you notice here we've used the letter a. The previous example we used the letter k. It's the same letter. We use A, we use K. Different books do it different ways. Our book is using a K. I don't care which letter you like. They mean the same thing. These are both the constant of variation. Whether you call the letter A, whether you call the letter K, it remains the constant of variation. Now in this particular form, it's real easy to see that if I solve for the constant of variation, I end up multiplying both sides by x, so I will get xy is equal to k. So what is that telling me? If I multiply two numbers together, I should get a constant. We're going to use that here in a few minutes. So when we are talking about y is equal to k over x, the words we use in writing say y is said to vary inversely as x. Those are the kinds of things we write in a word problem. These are the words that tell you that this is inverse variation. All right, let's look at a couple of things here on this graph. A couple of things I want to bring up. Of course, this is the x column, this is the y column. What's going on with x? If you look at it, every x value is increasing. X is going up. We started at the origin, and we're going up in x. But what is happening to the y value? Y is going down. Okay, this is one of the hallmarks of inverse variation. Now, let's take a quick look at plotting of these points. I have a graph to the right. If I plot an x-coordinate of 3, I get a y-coordinate of 8. If I plot an x-coordinate of 6 and a y-coordinate of 4, 12 and 2, 1 and 24. Now, we've seen that graph before. We're going to give it a name here again in just a second. But this is what happens with inverse variation. My graph comes down from an asymptote and usually ends up at another asymptote. It is a decreasing function. So there's our graph. Now, just a second ago, we said that x times y should equal my constant. Let's see if that really happens here in this problem. If I multiply x times y, what do I get? 3 times 8, 24. 6 times 4, 24. 2 times 12, 24. 1 times 24, 24. My constant of variation is 24. That means that this graph that we have on the right is the equation y equals 24 over x. Now, that graph right there, we've seen part of it. We've seen it with a little bit more to it, but when I talk about y equals k over x, this very much is what we saw when we looked at the parent function of y equals 1 over x. Remember, we called that the reciprocal function. Okay, the reciprocal function. That's what this is. The reciprocal function, only I have limited the graph to the first quadrant because it's real world. This is the reciprocal function limited to the first quadrant. Now, when we do this, when we use the reciprocal function, we do use the inverse variation, most of the time it is in quadrant 1. If this is a real world problem, I end up in quadrant 1. I will pass through a point, which is x comma a over x. And if you look at our graph looked like this. What is our end behavior? As x goes towards positive infinity, what is happening to y? Well, y is approaching 0. As x approaches 0, because I can't go beyond it, what is happening to y? Y is increasing to positive infinity. So we have some end behaviors going on here. All right, if AB is on the graph of an inverse variation equation, what's another point on the graph? How do you know? Well, we just said that A times B has to equal a constant. What order can I write AB in and get a constant? I can write it as BA. Do I not get the same constant from that? Does not B times A equal that same K? So a point like AB has a twin that is BA. Both of those are on the graph of y equals k over x. They are both points on the graph. All right, a couple of quick examples. Boyles Law said that the volume of gas held in a container at a constant temperature varies inversely. There's our words. Varies inversely with pressure. Now that's an equation writer. Volume varies inversely with pressure. There's my equation. Now the volume of a particular gas is 8 liters. 8. At a pressure of 3 pounds. With that information, all of this stuff is a point. This is the point. in this case 3 comma 8, allows us to calculate k. 8 times 3, k is 24. So what is the equation of this particular gas? Volume is 24 over the pressure. So now I can use that equation to solve for volume or solve for pressure for this particular gas. So the next question, part of the question says, what is the pressure when the volume is 6 liters? So I know that 6 has to equal 24 over P. Think about it as cross-multiplying if you want. 6P is 24. P is 24 over 6. So the pressure is 4 atmospheres. Don't forget about your units. All right, so how do I know if I give you a bunch of data, do I have direct variation? Do I have inverse variation? Well, there are clues that I look for. First thing I do is I look at the data itself. What's happening to X? In this particular case, X is increasing. What's happening to Y? Y is increasing. Anytime both X and Y are increases, you may have direct variation. The only option that you have is this direct? That's the only possibility. You may not have anything, but you may have direct variation. So how do you know? Okay. With direct variation, we had y is equal to kx. Solve for k. K is equal to y over x. So if I divide y by x, I should get a constant for every one of these points. Where are the points? Here's a point. Here's a point. Here's a point. I should get a constant for every one of those points. So if I divide 1.5 by 5, or sorry, 1.5 divided by 0.5, I get I get 3. There's my number. I get a 3. If I divide 6 by 2, I get 3. If I divide 18 by 6, I get 3. All of them are the same value. I get a k of 3. So that says that this is indeed direct variation. It tells me that the k is 3. My function has to be y equals 3x. Y equals 3x. It's direct variation. All right, the next one. What's happening with x? It's going up. What's happening with y? It's going down. Now, this may be inverse variation. I don't know. I have to confirm. And we know in inverse that x times y is equal to my constant. So I am going to multiply x times y. So I am going to take 0.2 times 12. I will get 2.4. I will multiply 0.6 times 4. I get 2.4. I will multiply 1.2 times 2. I will get 2.4. All of those constants are the same. This is inverse variation. The product of each pair is 2.4, so k is 2.4. So my final function is y is equal to 2.4 over x. right, let's look at the third example. X is increasing, Y is decreasing. This may be inverse variation. Let's check out X times Y. I need to know that X times Y is a constant. 1 times 2, I get 2. 2 times 1, I get 2. 3 times 0.5 is 1.5. These constants, or these numbers, are not the same. Therefore, this is not inverse variation. It's not direct variation, and it's not inverse variation. It's just a relationship. It is neither. All right, the last little bit. I want to talk about words that we use in problems. Sometimes more than one letter besides X and Y can be involved in this little game. So I want to take a look at how and what the words are that we are using. Here's an example that says Z varies jointly with X and Y. Now that word jointly means together. So this is saying that Z varies jointly with X and Y, so I get Z equals KX times Y. The next one says Z varies jointly with X and Y and inversely with W. So I get Z varies jointly with X and Y and inversely with W. And I have my constant of variation. The last one says Z varies directly with X and inversely with the product of W, Y. Z varies directly with X and inversely with W, Y. So those are some of the words we use to write our equations. So you can use that in a word problem to help you write your equation.